So the first four elements, if you imagine this starting at 0, our counter equals 0. So this is state 0 first. So we're talking about this first constant. We are running this function to get these first four elements. So we'll run it at 0 and get 0 and get the first 4 bytes. Then we'll run it at 1, get the second 4, run it at 2, get the third 4, run it at 3, get the fourth 4. And then we'll have our full constants complete. Next, we will be doing our key. So we'll take the key material. It's roughly the same idea, but we're addressing 8 elements instead of 4. We'll start our counter back at 0 because we are moving on to a different constant that we're reading from. So from 0 to 8, well, it's less than 8, so to 7. We will take our state at and we will load the key material. And we'll use the same pattern we used for the sigma constants. And, well, I said it's the same pattern. If you look at this and you say that this is state I and this is state for u plus I, that's because we already wrote over the first initial portion with this. So these first 4, we don't want to accidentally overwrite those with the key. So this function, or this loop, will cover these first 4. This loop will cover these next 8. And finally, we need to place our counter, nonce, and nonce. We could do a loop for this. I'm going to go ahead and just do it manually. So we can just literally call out that our state at position 12 here is our counter. And we pass that straight in, so that's fine. And it's already a 32-bit uint, so we're ready for that. Then we will need the states 13, 14, and 15. So at state 13, we're going to want to make another 32-bit word. And remember, these are our nonces. So we loaded our sigma constants, we loaded our key, and now we're going to load our nonce at position 0. Then we'll just copy that. So we will want to load state 14 and 15 from the nonce at 4 positions down. Okay, so this is our full, did we lose our closing bracket? Okay. That should be correct. So when we initialize the state, we're passing in this, which will be empty at first. We're passing in a key, the counter, and then we're passing in our nonce. Then we're taking that first row, loading it up with the sigma variables. We're taking the second 2 rows and loading it with the key material. We're taking that last row, first element is counter, next 3 elements are the incrementing portions of the nonce. All right, and next we're going to need our block function. So this is going to be essentially giving us the result. So we will make our own kind of return type here, and I'll show you why later. Block. And we will need the key, which will not change, so it'll be a constant. And it will be of our XCP chacha20 key size. Ooh, a comma after that. Then we will need our counter, Then we will need our nonce. And it will be of the predetermined size that we put up top. And then finally, we'll need where we're going to put our output. Okay, so what are we passing in here? We need our state. We need another copy of the state as kind of like our working copy. We'll need, let's see, okay, so we know that we use uint32s for the state. We'll do a working copy. We'll need a counter, unsigned. So there's a little bit of error handling we're probably going to want to do here. So if anything that the user passes in is null, we want to throw an error because we don't want to corrupt the data or encrypt the data with a key that they're going to lose access to because it was an ephemeral state. So we'll say we can do this as one big block. So if any of these conditions are true, then we will return an XCP parameter error. We can just call it a param error. That's fine. So what are the conditions we want to be careful of? The key cannot be null, the nonce cannot be null, and the output location cannot be null. So if the key is null or the nonce is null or the output location is null, then we want to throw this XCP parameter error. Now, if none of those are null, we're going to skip right on past that, or the program proceedings will skip right past that, and we're going to want to make our initial state. So this is our chacha20 initial state. And we need to pass in the state, the key, the counter, and the nonce. So we get the key, the counter, and the nonce from the arguments into this block function. So state, key, counter, and nonce. Then we want to copy the state into the working. So we want to copy the state into the working. So we're going to mem copy. Now it is destination and then source and then length of the order of the operands. So destination is working, source is state, and then memcopy wants to know how many bytes we want to do. So we're just going to do the size of working. And that's so that we don't overrun. You don't want to copy more bytes than you're allowed to copy because depending on exactly what architecture and system and operating system you're on, you'll either write into somewhere you're not supposed to be writing, or you will just lose everything you write that the operating system doesn't let you write past that point. You'll be expecting something to be past that point and there won't be anything. So we have our working state now, and what we need to do is our rounds. So we will pass our chacha20 rounds, and the only parameter is our state. Our working is the copy of the state we want to actually be affecting. And then we just want to feed this into the output. So it's 16. So I equals 0, while I is less than 16, we will increment I and store in 32-bit words into the output. So we want to take the working and state together. So remember, we take our, or you could, we called this working and state, but essentially our final output is our initial state that we're keeping and not destroying. So we have our state and our working, which here we called our initial and our mixed. So once we get done with this work, the rounds, we want to put the output bytes together into words and blend them state plus mixed. So we'll take our XCP, store 32, and we need, that is output. So we're taking our output and we are adding our working to our state. Okay, perfect. And then we will just need to return that everything worked okay. So we'll return XCP is okay. And did I get rid of the, nope, okay. So this is now our block function. We take our initial state and our working state. We check for null parameters. We initialize our working state. We initialize our state. We copy our state into our working state. We complete the work. And then we do modulus addition on the output for the output matrix or output result. The last thing that we will need